All right, here we go. Finally, we're getting to it, the unit circle. So with the unit circle, a lot here as a reminder. This is, we could think of this as a foundation or as a frame of reference, a system that we'll be working through. So it may not seem very practical to begin, but as we continue with talking about the unit circle, especially as we move into second semester, it'll start to show more of its value, more of its practical use. So it'll feel abstract, but that's okay. So we're going to skip this big picture that is our unit circle to start, and we're going to come back to that. So we'll start down here. So a lot of the ways that we frame or create the unit circle is by using triangles. So it says consider an acute angle theta in standard position. So right here, standard position, remember, means initial side on the positive x. Choose a point P with coordinates x, y. So that would be, if we're representing it visually, that'd be this point here. On the terminal side, so there's our terminal side, and draw a right triangle. So we've done all that. Again, if this point represents, we call this point xy, then the adjacent side of this triangle, so this side adjacent to theta, has a length of x, and the side opposite theta has a length of y. In this situation then, the length of our hypotenuse we're going to use as, or represent as, r. We usually use r to represent radius. That's going to come into play in a bit. Which we could determine the length of r, our hypotenuse, by using the Pythagorean theorem. Remember, a squared plus b squared is c squared. Or in this case, it'd be x squared plus y squared is r squared. Where a and b represent your sides, c represents your hypotenuse. Which then we could figure out that distance by taking the square root. So we'd have r equals the square root of x squared plus y squared. And we can do this for any angle in standard position. So it says for any angle theta in standard position, any point xy on the terminal side of the angle that is r units away from the origin, we can identify sine, cosine, and tangent. So if we're thinking about these, going back to here, if I wanted to identify the sine of theta, remember sine is opposite over hypotenuse. The sine of theta then would be y over r, opposite over hypotenuse. The same idea would follow for any angle. So even if we have an angle, like here, I know it's a little hard to see, that's large like this, we can still find that angle in the same way by using trigonometry. So again, this isn't a right triangle here, so technically what we'll be using is this triangle over here. But the way that we determine or find these values is still the same. It's still going to be opposite over hypotenuse for sine, so y over r. It's still going to be adjacent over hypotenuse for cosine, so x over r. And again, so this is coming from, remember, right triangle trig, so SOHCAHTOA. Tangent would be opposite over adjacent, so our opposite side is y, our adjacent side is x, so y over x. Cosecant is the reciprocal of sine, so r over y. Cosine, the reciprocal, or secant's the reciprocal of cosine, so r over x. And cotangent, the reciprocal of tangent, so x over y. So keeping that in mind, let's do a couple of examples to try and kind of apply this. So it says find sine, cosine, and tangent of any angle theta in standard position whose terminal side passes through the point P. So P is negative 5, 12. So x would be negative 5, y would be 12. Remember, sine of theta we represent as y over r. So we have to figure out what our r value is. Remember, we determined that already. We can find r by taking the square root of x squared plus y squared, so using the Pythagorean theorem. So x squared would be negative 5 squared, y would be 12. So 25 plus 144. 25 plus 144 is 169. The square root of 169 is 13. So r is 13. So y is 12, r is 13, so the sine of theta would be 12 over 13. Cosine of theta would be x over r, so negative 5 over 13. And tangent would be y over x, so 12 over negative 5. Or we usually put the negative up top, so I'm going to write it as negative 12 over 5. Okay. Same idea would apply for B. So we have our point at negative pi 2. So we want to find r, so that'd be the square root of negative pi squared plus 2 squared. So the square root of pi squared plus 4, which there's not really a way we can simplify that. Remember, you could not write this as like pi plus 2. You can't just take the square root of each individually. Can't do that with addition. If it were 4 pi squared, then sure, you could write it as 2 pi, but you can't do that with there's being addition. So let's just write it as is. So sine of theta would equal y, so 2 over r, square root of pi squared plus 4. Normally, we'd like to rationalize the denominator. For the sake of time, we'll forego that. Cosine is x over r, so negative pi over square root of x squared plus 4. Tangent would be y over x, so 2 over negative pi. Again, there are ways we can simplify, make these all a little cleaner, but we're more using this as a tool here. Okay. So you may be wondering, thought we were going to talk about the unit circle. Why are we talking about triangles and right triangle trig and all this stuff? Well, the way we construct our unit circle is by using triangles. So essentially, the unit circle is just a circle with a radius of 1. So if that radius is always 1, then r is always 1. So if our r value is 1, then sine of our angle is always just going to be the y value of that point. Cosine of our angle is always just going to be the x value of that terminal point, because it's just going to be y over 1, x over 1. So really, the key takeaway here is that for any angle in standard position, any point pxy, any point xy on the terminal side of an angle, cosine is just going to be the x value, and sine is just going to be the y value. So this is for the unit circle. So the reason for that again, so sine of theta would be opposite over hypotenuse, which would just be y over 1, or just y. So the same idea would apply for cosine. Cosine would be adjacent over hypotenuse, so x over 1, since r is 1, or just x. So with the unit circle, if I'm asking, what is the sine of theta? All we would need to know is just what is the y value of this point. If I want cosine, what's the x value of that point? So you don't technically have to know the hypotenuse, really, other than the fact that it's just 1. And with the unit circle, it's always going to be 1. Okay. So with the unit circle, there are essentially, again, I've talked about how we construct the unit circle using triangles. There are three special triangles, which are three that you've definitely seen before, that construct our key points, our key terminal points, or x and y values on the unit circle. And those triangles are 45, 45, 90, 30, 60, 90, and 60, 30, 90 triangles. So what I'd like us to do is determine, so if this were the unit circle, so let's pretend all of these have these coordinate planes here. What would our terminal point be? So remember, the length of the hypotenuse is 1 since we're talking about the unit circle. So we're focusing on the unit circle, so that hypotenuse is always just going to be 1. And we can try, at least as best we can, to construct or find these other values. So let's think about it this way. So we have 45-degree angle. So let's say I want to find, well, we've been using x and y like this to represent our x and y values for our point. So let's say I want to find y using this angle here. Well, we know this angle, we know the opposite side, we know the hypotenuse. So we can solve for this side by using right triangle trig. So I know the sine of 45 degrees is going to equal y over 1. So if I can figure out what the sine of 45 degrees is, then we can write that. Okay, sorry, I had to go grab a calculator. All right, so one thing to note is since we are thinking about 45 degrees, it would be helpful to make sure we're in degree mode. So the way we do that is we click mode. And we have radians or degrees, so we're in degrees, so we're good. So y is essentially equal to the sine of 45 degrees. So we get sine of 45 degrees, or y, is 0.707, rounded. That value, there is a way we can represent that as an exact value. So sometimes we might try and do that by a fraction, which in this case it doesn't work. That's because we have a radical involved, unfortunately. So I wonder if we could figure out particularly what that radical would be. So let's think a little further. So we know the sine of 45 degrees would be y over 1. In the same way, if I focus on this angle, the sine of 45 degrees would also be x over 1. So what this is showing is that both x and y are equal to the sine of 45 degrees. So x and y are equal. So let's think in terms of Pythagorean theorem. X squared plus y squared equals 1 squared. Sides squared equal hypotenuse squared. So we have x squared plus y squared equals 1. So we want to figure out, well, essentially, x and its y are equal, so I could write this as x squared plus x squared equals 1, or 2x squared equals 1. Divide both sides by 2. I get x squared equals 1/2. Take the square root, and we get x equals the square root of 1, or 1 over root 2. Which, let's simplify, so multiply top and bottom by root 2, and we get root 2 over 2. So what I've just determined is that x is equal to the square root of 2, and I know x and y are equal, so they're both the square root of 2 over 2. Since they're both equal. So since x is equal to root 2 over 2 and x is equal to y, they both have to be equal to root 2 over 2. So what I've determined here is that if I'm on the unit circle and if I have a 45-degree angle, my x value and y value of this triangle are both positive root 2 over 2. So what that means then, in thinking about our unit circle, is that since sine of theta equals y and cosine of theta equals x when we're thinking about the unit circle, what that tells us essentially is that sine of theta, or sine of 45 degrees, is root 2 over 2, as well as cosine of 45. Okay. So let's continue. So next we have down here, we have 1. So again, we have an x and y value. Let's try and give myself a little more space. So we want to determine what are those x and y values, and let's try and think about that. So we've got, well, sine of 30 equals y over 1. Cosine of 30 would equal x over 1. So sine and cosine are equal there. And this one may be a little more challenging for us to get through, or at least to construct, just because we don't know necessarily that x and y are equal. But let's see if we can get a little help with our calculator here. So when we did the last one, it was a decimal. It wasn't very helpful for us. So let's just try one of these, see if maybe this is something our calculator can help us with. So let's do the sine of 30 degrees. 0.5, that's pretty nice. So that's one that's already completely rounded. We could write it as a fraction too if we want to. I like to because I like fractions. So it's 1/2. So the sine of 30 is 1/2, which means that's my y value. Y equals 1/2. So this angle here, or so that side there would be 1/2. So we should be able to figure out what x is now, using again the Pythagorean theorem. X squared plus y squared equals 1 squared, since 1's our hypotenuse. So y squared is 1/2, so we can substitute that in. 1/2 squared is 1/4, because 1 squared is 1, 2 squared is 4. Subtract 1/4 from both sides. We get x squared equals 3/4. Take the square root. We get x equals the square root of 3 over the square root of 4, which is 2. So x is root 3 over 2. So what I just found is that with a 30, 60, 90 triangle where theta is 30 degrees, y is 1/2, x is root 3 over 2. So lastly, part C, we have another triangle here. It's another 30, 60, 90 triangle. So at this time, we're just thinking about theta being 60 degrees. So we still want to find x and y. But as you can see, it's the exact same triangles that we have up here. It's just been rotated or flipped. So the side measure across from 30 degrees over here was 1/2. So that would be the same over here. The side measure across from 60 degrees over here was root 3 over 2. So that'd be the same over here. So again, they're the same triangles, just oriented differently. One just turned. So this triangle is basically just kind of flipped and turned. So the hypotenuse is still the same. It's just our 30 degrees is now up here, 60 degrees down here. So our sides are still going to be the same if our 3 angles are the same and we have one same side. It's like a side angle side congruent triangles. Throw back to geometry there. Okay. So these points all kind of revolve around this Pythagorean theorem idea, that x squared plus y squared equals 1 squared. And we could always determine that points are on the unit circle by keeping that in mind. So like down here, I have 4 over 5, negative 3 over 5. So like this point, it says show that the point's on the unit circle. So I can always show that a point's on the unit circle by proving that this is true, that x squared plus y squared equals 1 squared. So if I take my x, y, my points here, and I want to show that they're in the unit circle, I would just make sure the left side equals the right side. So on the right, 1 squared is 1. 4 over 5 squared would be 4 squared is 16, 5 squared is 25, negative 3 squared is 9, 5 squared is 25, 16 plus 9 is 25, and 25 over 25, well, that's 1. So it checks out. When I square both these and add it together, I get 1. So in proving that it's on the unit circle, I'm showing that the hypotenuse of these two coordinate points or coordinate pieces, this terminal point, or the hypotenuse of the triangle created by this terminal point is 1. And you can always do that for anything here. So like for number 2, if I want to show that this is on the unit circle, remember we just want to make sure and prove that the hypotenuse is 1. So let's make sure that this checks out. So negative 5 squared is 25, 13 squared is 169, 12 squared is 144, 13 squared is 169, and 1 squared is 1. 25 plus 144 is 169, so 1 equals 1. So that checks out. Okay. All right, let's circle back to the unit circle. So this is our standard unit circle. It's big. There's a lot going on. So there are a few things for us to talk about. And what we've done today, or really the focus, has been kind of working our way up to this point. And there are a few different important pieces of the unit circle. So there are some blanks to fill in. So these blanks on the edges, these are our terminal points. So again, it's called the unit circle. So we know the distance from our origin here, so this is 0, 0, to all of these points is going to be a distance of 1. So what we have on the edge are the terminal points created by these triangles. What we have on the inside are radian measures and degree measures. So I'm going to start by showing our degree measures for the unit circle. And there may be some we know already. So like we start at 0 degrees. So an angle here would be 0 degrees. An angle, if we were to go all the way around, would be 360 degrees. Try to zoom in. This angle here, up to our positive y-axis, well, we know that's a 90-degree angle here. This angle, so it's all starting in that standard position. All the way around here is 180 degrees. All the way around is 270. And we've already done 360. So continuing, we also have these points halfway between, or these angles halfway between, like 0 and 90. So half of 90 is 45, so this is a 45-degree angle. Halfway between 90 and 180 is 135. Halfway between 180 and 270 is 225. Halfway between 270 and 360 is 315. So all of these have a distance of 45 between them. 0 plus 45 is 45, plus 45 is 90, plus 45 is 135, and so on. Our other key angles come in increments of 30 or 15. So really, actually, so they're 15 as in distances from the 45 to each of those. So 45 minus 15 is 30, 45 plus 15 is 60. But if we focus on every angle here on the unit circle, excluding those 45s, it's 30 degrees between. So 0 plus 30 is 30, plus 30 is 60, plus 30 is 90, plus 30 is 120, plus 30 is 150, plus 30 is 180, plus 30 is 210, plus 30 is 240, plus 30 is 270, plus 30 is 300, plus 30 is 330. So these are all of our angles in degrees. We'll come back to radians, but what I want to talk about here is how we come up with these terminal points. So the ones on the edges or on our axes are the easy ones in the sense that we think about this as a coordinate plane. So again, like this is an x-axis. and this is our y-axis. So we could extend those. So this point here, if it's a unit circle, that means the radius is 1. So we have 1 on the x and 0 on the y-axis. Here, again, our radius is 1. We're just going straight up. So we're on the y-axis, so our x value is 0, y value is 1. Here, we're going to the negative x-axis. So we'd have negative 1, 0. Here, we're going to the negative y, so 0, negative 1. So it's on that xy coordinate plane. We can determine these other points by thinking about these special triangles. So, for example, we have a 45, 45, 90 triangle, which, if we think about this point here and the triangle it creates, we have a 45, 45, 90. And we've determined previously that when our hypotenuse is 1, which is what we have, it's the unit circle, then xy is root 2 over 2, root 2 over 2. Similarly, when we have a 30, 60, 90 triangle, like here, where we have 30 degrees, 60 degrees, and 90, our x and y value are root 3 over 2, 1/2. And lastly, when we have a 60, 30, 90 triangle, our xy is 1/2 root 3 over 2. And the same types of triangles will apply in the opposite quadrants. So here's quadrant 1. In quadrant 2, let's think about whether x is positive or negative. So in quadrant 2, we're to the left of the y-axis, so our x values are going to be negative, our y values are going to be positive. But these angles are all going to be the same. So like if we think about this triangle here, we have, this is going to be 30 degrees because the distance from 180 to 150. This is going to be 90. This is going to be 60. Well, we determined with 30, 60, 90, we have an x value of root 3 over 2 and a y value of 1/2. The only catch here is that in this case, our x value has to be negative because we're in the negative we're on the negative x-axis. Our y value, though, stays positive. And the same would ring true for our next point here at 135 angle. So that's a 45-degree angle. So we have a 45, 45, 90. So with 45, 45, 90s, x is root 2 over 2, y is root 2 over 2. But we have to think about location. Again, negative x, positive y. So we'd have negative root 2 over 2 and positive root 2 over 2. Same applies here. Quadrant 1, 1/2 root 3 over 2, negative 1/2 positive root 3 over 2, because it's got to be negative x, positive y. And we can think about the same ideas here as we fill in the bottom. So in quadrant 3, both x and y are negative. So we'd have, instead of positive root 3 over 2, 1/2, we have negative root 3 over 2, negative 1/2. Instead of positive root 2 over 2, root 2 over 2, we have negative root 2 over 2, negative root 2 over 2. Instead of positive 1/2, negative root 3 over 2, we have negative 1/2, negative root 3 over 2. Same applies over here. Instead of positive root 3 over 2, 1/2, here we're in quadrant 4, where x is positive and y is negative. So we'd have here, root 3 over 2, 1/2 would be positive root 3 over 2, negative 1/2. Instead of positive root 2 over 2, positive root 2 over 2, x is positive, y is negative. Same would apply for our last. So notice those 3 points, they all apply. They're all 30, 60, 90 triangles, just at different points along our unit circle. The last thing we have to talk through around here is radians. So remember to convert from degrees to radians. We multiply by pi over 180. So you could do all of your conversions there. So we should get pi over 6 for 30. Here we'll have 0 and 2 pi. Pi over 4 here. Pi over 3 there. So you can pause the video, convert all of those. Okay, we're back. Let's check, make sure we've got all these down. Pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, pi. And on the bottom, 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2, 5 pi over 3, 7 pi over 4, and 11 pi over 6. Okay. So that's a lot, but that's the unit circle. This is something we'll continue to practice. I know it's a lot to take in right now, but here we go.